To today's webinar on multidimensional testing with business system integration. We appreciate you taking the time to join us today. First, I'm going to go over a couple logistical issues for today's webinar. It is scheduled for 1 hour. If we have a lot of questions, that could potentially go past the 1 hour, but we will definitely cover all of the content in the next hour. All participants have been muted for this webinar, so please be sure to type in any questions you have in the GoToWebinar system. We would like to get your questions throughout the webinar. If we can, we'll stop and get those addressed. If not, we will definitely cover them at the end. So again, please be sure to text in your questions in the GoToWebinar system. We are recording today's webinar. We will post this to our website within 48 hours, so please look for an email with a link to that recording. Please know that as a participant in this webinar, someone with Smarter Solutions will be giving you a call. If you do not want to talk to us afterwards, please just let us know in the feedback survey when you exit the webinar. I will now introduce Forrest Breifogel, our presenter. Forrest is a professional engineer, ASQ Fellow, and serves on the Board of Advisors for the University of Texas Center for Performance Excellence. In 2004, he received the Crosby Medal for his book, Implementing Six Sigma Second Edition. He recently was named the 2011 Quality Professional of the Year by Quality Magazine. He has authored or co-authored 13 books and published over 100 technical articles for well-known, well-read publications, and he is the founder and CEO of Smarter Solutions. Again, thank you for joining us, and I'll now turn it over to Forrest.
Okay, thank you, Mallory. Looking forward to this session. We're going to be covering something that's a little bit different than is normally covered. I refer to it as PassFail functional testing or multidimensional testing. First, I'll be describing the methodology, and then I'll be talking about some example situations that you might encounter to apply these techniques. If we go look at the type of responses that we typically get, it boils down to basically continuous, attribute, or something else that I call logic pass-fail situations. So we're going to be focusing on the latter one this time. But first, let's consider what kind of responses might we get. Well, first off, continuous would be something that we might measure. A part, for example, it's going to have a dimension. We've got to find enough measurement in the instrument. We get down to 1/10,000th of an inch, perhaps. Or we might look at how long it takes for a particular transactions to get completed. So those are situations that would be a continuous response. Now, another situation is an attribute response. We might put 1,000 sheets of paper through a copier, and then one of those out of 1,000 jams. So the failure rate would be 1 in 1,000. Or we might have transactions that we put through our process, and we have out of 10,000, we maybe have 3 that fail. So it would be 3 out of 10,000 would be our failure rate. So the idea with this is we have a transaction that either fails or it doesn't fail. Now, logic pass-fail testing or logic pass-fail situations is similar to this, but it's a little bit different. In this particular case, we'll have a failure. However, we're going to always have a failure. So in this situation, we might have in a computer in our office, it fails when we have this particular word processor application, and it runs in conjunction with a certain printer, and then maybe we have something else attached to it like a plotter. I'll have to apologize a little bit here. Some of the examples that I'm going to be sharing with you is somewhat dated. This book was, I covered this techniques in Implementing Six Sigma Second Edition, so some of the examples are somewhat dated, but hopefully you can bridge it to today's technology that we might have. But in logic pass-fail situations, we'll have a particular combinations of factor levels, and we're going to have it so that they pretty much always fail when we have this set of conditions occur. So that's where logic gets involved in this. So as I said, we're going to be focusing on logic pass-fail problems. So before we get started, I'd like to ask a question. It's basically the amount of training that you've had for this type of situations. So please respond to the questionnaire. Okay, it looks like about getting close to about half of you voted. A couple more seconds. Okay, let's see what we got here. Okay, it looks like we've had on-the-job training with some of the people and none for others, and so it's somewhat of an even distribution here. Okay, I appreciate your response to this question. So let's look at a particular situation. You have to go in and test a new computer function. On the left-hand side, you'll see 7 different factors that we want to consider in this test. Now, each of those factors can take, in this particular situation, 2 different states. So, for example, network, we can have type X versus Y. Or we might have a small memory or a large memory. So our job is to basically test this particular function. So the type of problems we're trying to capture is maybe network type Y. Whenever the memory is small and there's a modem, it doesn't work very well. So if we would go back and look at our test possibilities that we have, the circled areas represent that particular situation. So as you can see, and can you imagine, there's quite a few different situations that this particular set of conditions could encounter. Now the question is, how do we test for these particular sets of conditions? How do we make sure that it works in the office environment that we might encounter for this particular set of software? Now if you look at how teams encounter this kind of problem or take on this particular situation, I've noticed several different approaches. One would be a haphazard approach. Now with this particular approach to addressing the problem, if the failure is detected, the testers really don't remember what they did that worked, because it's not only what failed but also what worked gives us insight to how well this software and this software-hardware integration is working. Someone else may undertake the problem using a very complex algorithm. Another team might approach it as a one-at-a-time approach. Try this, then that, and so on. Another team may look at all possible combinations. So you can see there's several different approaches different teams might take on for addressing this particular problem. Now, if we look at these strategies, they really do not have an easy general process or approach that has general applicability. Also, we often don't really have stopping rules. Whenever we run out of time, let's stop the test. Also, we don't typically have test coverage. So we may have done a lot of tests, but how good a job do we do relative to how the product will perform in a customer environment? So what we'd like to have is a fish approach that is structured and could be explained and used by others. Now this overall methodology could be considered a control mechanism within the overall development process. So we'd like to have a system basically within the overall development testing process so it's not dependent upon the individual that's actually conducting the test or putting together the test strategy. So a structured approach could be used to could involve use of design of experiment matrices. Now with design of experiments, we might have 8 trials that are listed here. So for trial number 1, we would be setting factor 1 to be the plus condition or the high condition. Factor 2 would be low condition, and so on. Now in traditional design of experiments, what we would do is look at this particular set of conditions and then monitor the response and record the response. So we might get an answer of 3.7. So if we did trial number 2, we might get an answer of 2.6, and so on. So basically for each of the trial conditions, we got a continuous response. However, for the logic pass-fail situation that we're talking about here, that's really not what happens for this particular test environment. What we'd be doing is running the various factor combinations and then observing whether the test works or it doesn't work. So for example, if trial number 1 works, we put a yes basically. And we go all through the various processes or various trials that we've got. And we might find, for example, trial number 5 doesn't work. Now the assumption that we're making with this forms of testing is that if trial number 5 did not work satisfactory, it will always not work satisfactory. Remember, we're talking about logic here. So we're talking about states in a computer. Now, if we use this approach, we can go in and still address whether we got combinational problems. However, if a trial fails, we really don't know why it failed. So for example, trial number 5 failed. We know that the product does not work as well as we'd like. However, we really don't know why it failed. Now, if we were interested in understanding why it failed, we would need to do a technical assessment. So perhaps if we were in the test organization, we might call the development team in there, and then they might examine it and figure out what the problem was. Now, in other situations, they may not be able to figure out what the cause was so that they could fix the problem in the development code. But if they can't, then we might be able to run additional tests to find out what's causing the problem. Maybe it's whenever A is high and B is low and D is high is causing the problem. The next question we might have is, what happens if there's no failures? Well, what we'd like to do is describe how good the test performs. We'd like to assign or make a statement relative to test coverage. Now, I'm going to describe test coverage a little bit different than what most of you may have seen in the past. Let's look at how somebody might describe a problem that they have with their computer. They say, whenever I do this and this and this, it doesn't work. There's a problem. They don't typically say, whenever I do this, then this, then this, then this, then this, then this, then this, it's a problem. It's typically maybe 3 or 4 statements or situations will describe their problem. So I call those situations or levels, the number that you have, as group size. So typically what I'll try to do is describe maybe how well a job do we do relative to combinational problems of size 3, or group size 3. The higher number, obviously, the better. So what I'm going to be doing, like I said, primarily focusing on maybe 3 or perhaps 4 to describe how good a job that we're actually taking on. Now the question is, how do we arrive at this particular number? So table 0 in implementing Six Sigma second edition yields test coverage as a function of various group sizes for this particular test design that we talked about earlier. So this is what Table O looks like in implementing Six Sigma Second Edition. Now for our particular situation, we had 8 trials, so that represents the black bar there. Now if we look at group size 3, we follow the black bar upward, and we see that we got 90% coverage. So if we had 7 factors in 8 trials, we would have 90% coverage of all possible combinations of 3 things. Now, that's really quite good. If we go through the mathematics of it, we see for group size 3, there's really 280 possible combinations. And we got 90% coverage in only 8 trials. So I think that's fairly good. Now the question is, you might ask is, how did you calculate 280? Well, this would be the mathematics that's shown right here. So the total number of combinations of factors for 3 for this particular situation would be 280. So again, we got 90% coverage of 280 possible combinations in only 8 trials. Now, you may not have 7 factors in 8 trials. You might have 5, 6, or 7. Well, in fact, the coverage is about the same no matter if you got 5, 6, or 7 factors in 8 trials. It just turns out that way. Now, for a given trial that fails, if you had 7 factors, there's lots more combinations or reason that it could fail than if you had 5 factors. But the actual test coverage turns out to be pretty close. Now, similarly, if we had 16 trials, we could actually have 15 factors, or 14, or all the way down to 8 factors. In that particular situation, we would have roughly the same coverage that it shows to be on that graph. You got 32 trials. You can actually have 31 factors. Down to 16 factors, again, you would have roughly the same coverage. Now, when a failure occurs? Like I said earlier, a combinational cause may be obviously if we get the right person to examine the particular situation that we've had. Or you can use a search pattern strategy to determine the root cause. Maybe a combination of factors that causes the failure. Got another question for you. Please select the frequency that you conduct these type of tests. Okay, we got about half of you voted here. Okay, let's look at what we came out with here. Okay, it looks like about 50% of you here never use this form of testing, and then we somewhat split between some and frequently. Okay, that's quite interesting. So we do have people that are encountering this particular scenario in their work, obviously. Well, that's great. So let's look at a situation here. A company is considering buying several new personal computers to replace existing equipment. So as we see that this technique is not necessarily just in the developing of software and hardware integration. The company has some atypical configurations. The company wishes to make a quick and dirty test to verify that the product will work with its peripheral equipment and software. So the company believes if there's no combinational problem with 3 factors, they're probably good to go. Okay, now we're going to set up the test. Well, there's 4 different types of printer. However, believed that if we could get it to work with these two printers, then it'd probably work with the other two. So that really describes how we might describe the space of printer coverage with only two printers. Some companies had an application where you might put two displays on it. There was concern that that may not work satisfactory. They had two different word processor packages and two different spreadsheet programs. You can see this is somewhat dated here, but anyway, bear with me there. Some individuals use plotters while others did not. Might have had two different network systems interconnecting the computers. So when you kind of put this all together, this is kind of what we came out with. You got the printers, and you got the two extremes there in the displays, and so on. So if we look at how we might test this, we could run it in 8 trials, because we got 7 factors and 8 trials. So for example, trial number 1 would be the set of conditions that we're showing right here. And the idea is that we would go in and test it to see if it performs satisfactorily with those particular set of conditions. What we're going to try to do is really stress that particular setup to see if it works in a real environment. Now, we can also get some other information out of this at the same time. We might want to look at the performance of the particular computer that we're purchasing. So we could still go in and record how well it's performing a particular set of conditions or particular software that we're running through it to see how its performance is tracking. And then we can analyze that separate from this particular test. Now the percentage of coverage would be similar that we had before. So we would have 90% coverage of combinational 3 problems. So if we ran through all those 8 scenarios and they all work satisfactory, we'd probably feel fairly good relative to whether the product will perform satisfactorily in our work environment, because we got 90% coverage of combination of 3 things. Now, if we wanted to have a higher coverage, then we'd need to run additional trials. Now the question would be, is what happens if we really had a printer X problems with 2 displays in network X? Would the particular test capture that problem? Well, the answer is yes, because trial number 6 would fail because of that particular set of conditions. So let's look at an example here. A program was written so that a computer terminal could interface with a link that is attached to a computer network. Again, we want a structured test for this particular example. Combinational problems with only few test cases, if at all possible. We want to make sure that it works in the abnormal environment. Because often what happens in the test environment, we'll say, well, this is what somebody's going to do very frequently. And so that's the tendency. The tendency is to test those particular scenarios. What we really like to do is to make sure that it works in these extreme conditions, because those are the ones that can cause us the most problems. So the following assumptions. We're going to use that fractional factorial designs in the tables in the back of implementing Six Sigma second editions. We're going to look at the extreme conditions that we might have for particular factors, and if it performs satisfactory for the extreme condition, we're going to assume that it performs satisfactory for the levels within there. So if an abnormal situation causes a failure, the trial will be reassessed without the abnormal situation. So if we get a problem, basically, we may have to go in and evaluate the whole matrix again to make sure that it performs satisfactorily. If we get a problem and we're fixing the code, because we could create another problem. So for this particular situation, we could run these particular factors. Now in this case, we said, well, we really got 4 different scenarios for the network adapters. So we could take 2 columns and combine them. So you got minus, 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 plus, plus, minus, plus, plus. So that's how we can get 4 different combinations. Now, our test coverage is not going to be as accurate as it would be normally, because that's calculated and assumed that you got 2 levels. But from a point of view of actually testing it, this is something that we could do. So this would be the design that we would have for this particular set of conditions. For our 16 trials, and we got group size 3, now we'd be following up the blue bar, we'd notice we get about 98% coverage of combinations of 3 things. As you can imagine, there's quite a few combinations of 3 things, but so we did a fairly good job here in only 16 trials. Now, one other thing I like about this overall methodology is it really works real well with teams. So now you can work with various teams to go in and pick the factors that you're going to consider, and then that can lead to also the levels of the factors that you're going to consider within this experiment that you're running. And basically it boils down to is breaking down some of the barriers that you can get between the various groups within the overall development process. Because everybody within these functions has a particular way of viewing the importance of particular factors and levels of the factors. And so now you can very easily put them together to go in and come out with a very good test on how you're going to be approaching these particular factors and levels of factors in this development test, in this verification test. Now what can also be done is that you can go in and build modules and then build a hierarchy of strategies. Because what I've been basically describing is kind of like a functional test at the end of the overall development process, but what you could do is build these matrices in various sections or pieces of the code and then kind of build them all together. And so now whenever you're getting to the end, you're really testing combinational areas of various functions that you're putting together at the end of the test. So the opportunities that you have is for system configurations, for microcode testing, for software, and also even if why does one system work and another system doesn't work. So now you can start interchanging parts or interchanging various components of these 2 different systems, and then can help you figure out what the particular problem is that you're experiencing. And also intermittent failure diagnosis. So all of a sudden we've got something that doesn't fail reliability. You might be able to start switching things around and be able to figure what causes a particular problem. Because one of the biggest problems that you have in the computer industry is no trouble found. So if we look at traditional functional tests, often leads to inefficient one-at-a-time approaches, we miss the combinational problems. Often we have tests that don't include coverage statements. So this overall test matrix approach can give a systematic approach for efficiently detecting these combinational problems. It also can utilize the team inputs to improve the scope of what we're actually doing in the test. So these are areas that can really help you, and also you can get into given test coverage statements, as I said earlier. So the application of this is in the development in designing product, peripheral equipment, and interfaces. You can also use it in manufacturing process quality and also dealing with supplier interfaces also. Now, one of the challenges that you have is what do you deal with, or how do you approach if you've got more than 2 levels for a particular factor. So for this particular situation, then we need to go in and use some software to help us out with that. So what I've put together, I got here is we've got a software package that can help for that particular situation. So if you look at what I've got right here, I've basically got a text document. In this case, I've got 11 factors. I've got this factor here is STMP, whatever that means, okay, to somebody. And then all these asterisk things are just kind of notes, basically. But this describes the levels that you have. So basically, what we have is one factor here that's got 2 levels to it. Okay. Now we got another factor we're going to call STG, and it's got none and it's got with. Okay. Now this factor here, DS, has 3 levels, and we're going to call them those names right there. Factor 4, called DSP, got none and with. Factor 5 got 2 levels. Okay, now factor 6 has 4 levels. And the same as goes for factor 7. And factor 8's got 3 levels. Got 3 levels for factor 9. Factor 10's got 2 levels. Factor 11's got 4 levels. Okay? So this is basically what we have here for our particular input to our design. So you could see how you could create simple text documents so that it creates in this form. And this is just syntax for this particular program. So each factor is separated by a space over here and a space there. We got a blank line here and a blank line here. Now what we want to do is take the program and we want to generate some tests. Okay? So basically what I had the program do is generate the tests. In this case, it's going to be 32 trials. Okay, that's the minimum number I can have for this number of factors and levels of the factors. So you can see now STEM is going to have none the first time. This is going to have none, and so on. And trial 2 has a different set of conditions to it. Okay? So if we're going all the way down here, we can see we got 32 sets of conditions for 32 trials. Now what we can do also with this software is that you might have some exceptions. So for example, factor number A when it's at level 3, and factor F when it's at level 2, and factor G when it's at factor 5, it's not legitimate. So you can put into the program exception files. So you don't have to have all combinations actually be valid. So the idea now is that we'd run this 32 set of conditions and they all pass. Now then, the question, if they all pass, then how good a job did we do? So that's where we go in and answer that by looking at the test coverage. So if we look at test coverage for 2, that's a combination of any 2 factors and picking one of the factors at each of those levels. How good a job do we do? Well, we basically got 100% coverage. So we got 100% coverage of combinations of two things. How about three things? Okay, we didn't do 100%, but we got 98% coverage. So you pick any three factors and then pick a level for each of those three factors, and you evaluate and see if it's there. We did 98% coverage of those. So let's see how good a job do we do on 4. So we got 91% coverage for 4. We did a pretty good job in here, even though we had only 32 trials, because we had 11 factors and several of them were not just at 2 levels. So that's what this multidimensional testing software can help you do, to go in and create the design, and then it also tells you what test coverage you would have. So you'd like to know what the test coverage is before you begin the experiment, obviously, and have everybody agree to them that this is a good, significant test for what we want to undertake, and then we undertake the test, and if they all pass, then we feel really good about the software that we're in software or software integration. We feel really good about the product that we're going to be offering. Now the question is, how does this fit into the big picture? Well, if people have been following me for a while, I'm big on the big picture, because a lot of times we get into silos, and what we want to do is still focus on the big picture, and that's really what we want to make a difference to. So if we went and looked at how we actually perform work, we can look at the value chain. So we got develop product, market product, sell product, produce, deliver, invoice, and collect and report financials. So if we look at any one of those functions, the rectangle boxes that we have, we then can go in and create the oblong boxes that describe the metrics that we're going to use relative to quality, cost, and time. So if we look at produce and deliver products, will be defective rates, lead time, WIP, on-time delivery period, constraint throughput, which is a financial metric. Now if we look at development product, we're looking at product development lead time and product development design quality. So that's what we really want to focus on improvement. And what I'm suggesting, this multidimensional testing can be part of the process within the development process, so that it improves the design quality, and also you can actually get more done with less. So you can actually do a better job relative to the metrics of your overall development product cycle. That's what I'm suggesting would be one application of these techniques. So kind of in summary here, we talked about the application of this PassFail functional testing methods, and we also described how you could actually put together these tests and get a response in addition to coverage statements relative to how good a job you did with the test.
All right, thanks, Forrest. As we mentioned before, this is now the time for questions and answers, so please type in any questions you have into the GoToWebinar system. If you have any specific scenarios that you would like Forrest to ask questions, or you would like to ask Forrest questions on, please feel free to submit them. If for some reason there is something that can't be covered in time or in complexity in this discussion, we can definitely address them offline. So please feel free to type in any questions you have. The first question for us is, can you again explain how multidimensional testing differs from the design of experiments techniques?
Okay, in design of experiment techniques, whenever you're running a trial, you'll get typically a continuous response. So the answer is 3.7, 2.8, or whatever. If you're looking at the significance of factor A, what you're really doing is looking at the difference between the averages when A is high versus A is low. So we're looking at a response, and then if that difference is large relative to air, then we say it's significant. So again, the response for a design of experiments is a continuous response. In the case of PassFail functional testing, we're just looking to see if the particular product in this particular configuration worked or not. It's a yes or no answer. It's not a continuous response. It's not, and it's also a logic pass-fail situation. So if trial number 2 fails, we're assuming it always fails. So again, design of experiments are doing a continuous response and looking at significance from the averages when factors are high versus low, looking at that difference, see if it's large enough to see if it's significant or not. This is trying to create a certain set of conditions so hopefully that they all work, and then we get a coverage statement relative to how good a job we did.
Okay, and the next question is, what can be done in the test if there are illegal combination of input factors?
Yes, for illegal combinations, you need to go into the software. You could say that A is high and C is low and D is high. That's an illegal combination. And what it will do is basically set it up so that that particular set of conditions don't occur within your design. And then you could also take that into account relative to the coverage statement.
Okay, and the next question, where can we go to purchase the software you demonstrated?
Yeah, you can go in and give us a call at the number that's listed right there, and then what we can do is better understand your particular situation, and then we can go in and take it from there, because it's more than just going in and buying a shrink-wrap copy of the software, because there's some tricks to the trade on using the software to utilize it to its fullest intent. So it kind of, we're looking at including some training along with the software.
Okay, and these are great questions, so please keep them coming in. Our next question is, we have a very large system of software and hardware components that we would like to get the best coverage possible with the least effort. Are there any tricks of the trade to enhance the testing's effectiveness for this situation?
There is most definitely. Because a lot of times what you'll have is, and that's part of tricks of the trade, is that some particular aspect of the design is not going to interconnect with something else. So what you can do is break each one of the components and maybe do a test of that, and then build this hierarchy. Or the other thing that you can do is to go in and design your tests so that you're actually doing 2 tests at once. In the old days when we had memory and memory slots, we were actually able to go in and do the matrix for memory slots, because even the slot position that you had the memory module in might have made a difference, or where you actually put the card in the computer might make a difference. And those things are really important. You could build a design separately and run the trials in conjunction, and so you could actually get a lot better test coverage. So that needs to be part of this overall discussion, and then you can build a hierarchy. Because the problem is, if you go in and take up especially a complex system like that and leave it up to one individual to put together a test and somebody else to put together a test, you can have something that's quite different. And what you'd like to do is have somewhat of a similar approach to undertaking this complex system, and that you can build upon the hierarchical nature of it, and also basically just putting it all together. And you're not waiting to the end of the test and find, oh my gosh, I got something that's a basic problem that we should have found a long time ago. And that's, basically where I'd undertake that particular situation.
Okay. Thanks again for participating in the questions. If you have a question that we did not get to, please feel free to contact us by phone, email. We will definitely want to follow up with you. If you could also, please be sure to fill out the exit survey at the end when you leave the webinar. We appreciate your feedback and want to hear from you. So again, we thank you for taking the time to join us. And if you have any other questions, please be sure to reach out. Thank you.